Okay, great. I'm going to begin lecturing. I cannot see people, so I can't really call hands. So if I ask questions, I encourage you simply to, well, let's see. Do we have hand reactions? Yes, we have hand reactions. So if I ask questions, please raise your hand in the normal way, and I will attempt to call on somebody in order to get answers, in order to give answers. Um, so last time we talked about linear programming. And techniques for using random sampling in order to speed up our linear programs. Oh, interesting. Sorry, let me change my display here. Let's see if I make it bigger. Sorry, I'm a little rusty on this, but it should only take a second for me to remember what I'm doing. Okay, there we go. Oh, admit all. All right, so we talked last time about linear programming, and we discussed a number of sort of elegant techniques for using random sampling in order to speed up linear programming. I described this SampLP algorithm, which is based on sampling d root n hyperplanes and recursing, and then adding some violating hyperplanes to your active set if it's not too many. And this, when we analyzed it, yielded a runtime of order d squared n log n, which is basically the work of checking for violators, violating hyperplanes and such, plus a term which was determined by the size of the recursion tree, which had this. Where's my eraser? Which was about 2 plus log d. So we had a runtime which was which is sort of polynomial in n for any constant d, but exponential in d. And then this relied on a sampling theorem, which said that if you sample R of n hyperplanes at random, then you get, where's my number? Right. D times m minus R minus 1 over, I just had this problem in d times m minus R minus 1 divided by R minus D violators. So if you choose about square root of n hyperplanes, then you get about square root of n hyperplanes, and everything works out very nicely. We then showed how to improve this with a softer approach based on what we call iterative reweighting, where we simply choose in each round just 9d squared hyperplanes. And then we double the weight of the violators. Again, if this weight is not too large. And we concluded that there's a 50-50 chance of this happening, thanks to our sampling theorem or to the generalization of it that you're going to prove in your homework. And that means that, and then we showed that since half of the iterations end up doing some doubling like this, you end up with just order d log after order d log n iterations. Make the weight of B of H larger than the weight of everything, which is a contradiction because these basis hyperplanes are part of everything, and so they can't possibly be, whoops, sorry, I have some late admits. These are the optimal hyperplanes are part of the whole, and so of course their weight can't be greater than the weight of the whole, right? And the reason behind this, the reason both of these works is that in both cases, both algorithms rely on the idea, why in the world is that happening? Both algorithms rely on the idea that some optimum hyperplane is always among the violators. And this is for the simple reason that if you don't violate any of the optimum hyperplanes, then you can't be better than opt. And so, in fact, you will be at opt already. So if you're not at opt, you'll have something better than opt. That can only happen if you're violating one of the optimum hyperplanes. So these are the two algorithms that we saw last time. Now we are going to and this algorithm had a runtime of order d squared n log n for just doing the iterations plus d to the d over 2 log n for doing the sampled problems. Notice that this algorithm is not really recursive because you immediately sample such a tiny number of hyperplanes that you're going to solve the problem basically by brute force. That's the d to the d over 2 runtime. So again, for constant d, this is order n log n. So it's as fast as convex Hull. It's a very simple algorithm. How could we possibly do better? Well, you can mix these two algorithms. Okay, this is along the lines of if you develop a faster algorithm for something, you should plug it in as a subroutine for whatever other algorithms you're using. What we do is we use recursion at the top level. We sample about square root of n hyperplanes at the top level. But we solve each recursive call with the iterative rerating algorithm. Why is this a good idea? Why is the iterative reweighting algorithm a bad choice at the top level, but a good choice at the next level? So what are the two terms in the original sample LP algorithm? There's this order d squared n log n term and this log n to the log d term. Where do they come from? Well, the d squared n log n, I've said, is the time spent working at the root of the tree, right? The log n to the log d term is basically because of the size of the tree, that it expands sort of super polynomially. So what do we gain by switching to the iterative sampling algorithm, to the iterated reweighting algorithm, once we go below the top level of the recursion tree? Yes, Balint.
I guess we can maybe avoid the recursive cost of the sample P. Like the overall thing will still be like n log. Oh, actually, maybe it won't be n log n because it might be like square. I think it will still be approximately n log n, like d squared n log n for the main term, but maybe the terms that depend on d will become a bit better since we
Well,
don't have
where is the second term coming from? Where is the log n to the log d term coming from?
from the recursion,
Okay,
which
so
we no
what
longer
is
do.
exactly? We only do one level of recursion, right? The d to the log n term came because we had a branching factor of, it was actually we had a branching factor of about d because we were doing sorry, wait. Um, yeah, we're doing about d recursive calls, right? One to collect each hyperplane. And then the subproblems are a size root n. So uh, we have this depth log n recursion tree, but its branching factor is d. And so it's d to the log n leaves. But if we instead of doing recursion on the second level, we just use the iterative reweighting algorithm, we no longer have this exponentially growing tree. We have a tree whose height is exactly 3, right? We have the root algorithm of sampling, which has d children. And in each of the d children, we will have square root of n, we will have, we'll be recursing on roughly square root of n hyperplanes, but we don't solve those recursively. We solve the root n hyperplanes using the iterative reweighting algorithm, which is not recursive. So it's only a depth 2 tree, or depth 3 if you consider the constant size problems that are solved by iterative reweighting. So the second term of the recursion up here goes away, right? We just have the d squared, we just have the work at the root, and then the work of the iterated sampling. Now, why are we bothering with using the sampling algorithm at the top level instead of using iterative reweighting from the beginning? Well, the advantage is that iterative reweighting kind of it's got a better, it doesn't have this recursive dependence, but it does spend a bunch of time growing the weights, which has this log n cost. So once you take that away, and you only run the iterative reweighting on the subproblems of size square root of n, you've got d of those. So you're going to you're going to do that slow growth of weights on d subproblems of size root n, but that's negligible, right? That's only d root n total size. So it doesn't really contribute a lot to the work. So this improves the running time to order d squared n plus d squared log n to the times d to the order d. Okay. Plus, uh, this is, again, we are running the iterated sampling algorithm on problems of size square root of n. So we get a root n log n, and that gets multiplied by the base case work, the size d problems in iterated sampling. So that gives us this d to the fourth term. But what's important here is that the leading term is now linear in n. It's not even n log n. So we're actually faster than convex Hull, um, even in higher dimensions. And this is because we're not trying to construct the entire hull. We're just trying to find a single optimal point. Okay? So that's kind of a summary of where we are, that we've managed to get all the way down to linear in n. But we still have this exponential in D problem. But it seems like we're, how much simpler could a linear programming algorithm be than this the two that, each of which take only 5 lines or so. So any questions about where we start from? All right. Oh yes, go ahead.
Would
Dubim.
would I guess like is this kind of the optimal I guess like level at which to start iterating or start doing the iterative rewriting or like would we go down
So
any
you're asking
farther?
if we should maybe do two levels of recursion before we switch to iterative reweighting.
Yes.
Right. So the thing to remember is that if you is that even the first level of the recursion is enough to make the total size of subproblems that we're tackling at the second level negligible,
Okay.
right? The total size of all those subproblems is already square root of n or so. So if we did another level of recursion, then the third term in what I'm showing in these notes would now become d to the eighth times n to the quarter or something like that, right?
Mm,
But it's already negligible. It's already basically dominated by the other terms, except for really weird values of d and n. So there isn't really a benefit to going another level of recursion before switching to the only reason that we have even one level of recursion is that the iterative reweighting is a little bit more expensive just by a factor of log n at the very top level when we're
I
dealing with
see.
n hyperplanes. So we use one level of recursion to do away with that.
Okay.
Okay.
Hmm.
All right. Any other questions? So the question on the table is, given how incredibly simple and fast this algorithm is, can we do better? Um, and surprisingly, the answer is yes, we can do better. There is an even simpler algorithm. And by itself, it is not faster, but it shows the way to getting even faster than these algorithms. And the beautiful, beautiful breakthrough here is due to Seidel. Seidel was also the one who developed that randomized algorithm for shortest paths based on witnessed matrix multiplication. He's a very important computational geometer. He also developed treeps, which are a very beautiful binary tree, sort of balanced binary tree data structure that have particularly good features for computational geometry problems. Seidel is a computational geometer. And Seidel realized that you can solve linear programming using a randomized incremental construction. Why sample a complicated way when you can do the simplest, obvious thing of a randomized incremental construction? So what would be a randomized incremental construction for linear programming? Right, remember randomized incremental construction for convex hull, we started with an empty set, we added points one at a time, and we maintained the convex hull, we updated it as we added each point. So what would be the analog for linear programming? Yeah, Dibum, go ahead.
Would we just like add in the constraints and then just re-optimize at each constraint and then add them
Exactly.
manually? Okay.
Just add hyperplanes one at a time and re-optimize when you need to, right? So there's two pieces to this idea. There's as with any randomized incremental construction, there's the hope that you don't have to update too often. And then there's the question of how much work you have to do the update. Yes? So our idea here is going to be to just add hyperplanes in random order and update the opt when you need to. So it's a two-line linear programming algorithm. What's beautiful is the analysis, which is basically a backwards analysis. And for that, I'm going to actually articulate the algorithm slightly differently. I'm going to say remove one hyperplane at random. Recurse. Put it back. And then update the optimum if necessary. Make sense as an algorithm? Clear?
I think it is not that clear how we would update the opt when we need
Yeah,
to.
there is that little detail. I'll have to get to that. Yes?
I guess my other question is like, is this like the backwards version of like the algorithm, or is this the forward?
Well, the
Version.
forward version, usually when you talk about randomized incremental constructions, is you say it's an iterative algorithm where I add one at a time, right? This is not literally a backwards analysis, but I've sort of restated it as, well, there's some hyperplane I'm going to add last. Let
I
me think
see.
about that first.
Okay.
That's why I'm calling it backwards. There's one I'm going to add last, and let me recursively think about doing all the other stuff before that.
Okay.
Okay. So, yes, Balint pointed out there is this problem. How in the world are you going to update opt if necessary? But let's do the easier stuff first. How often is it going to be necessary? What is the probability that I'm going to have to update opt when I add that last hyperplane? Well, let me turn it around. Oh, sorry, go ahead, Nikom. Nikom? Is that your name or is that just your handle? I'm not hearing you. You should need to work on your mic, I think. Anybody else? So let me turn it around. Under what circumstances will I not have to update opt when I add the last hyperplane? Valent?
So d over n of so d of the hyperplanes actually like affect the opt. So if the final one you pick is not one of those constraining hyperplanes, then you will not have to update it. So the
Exactly. I
probability
won't have to.
is
The point is that if I already found opt, I won't have to update it, right? If the optimum is already there generated by the first n minus one hyperplanes, then I don't need to. Then I'll already have found it, and my last hyperplane won't violate that optimum, and I'll know I'm at the optimum already. So you then answered the next question, right? What does it mean for the opt to be found among the n minus one previous hyperplanes? Well, it just means that the d hyperplanes that define opt were already among the n minus one previous hyperplanes. So the only way that things can go wrong is if some h in the basis is the last hyperplane, right? But since I'm adding the hyperplanes in random order, which hyperplane is last is random. So the probability that the last hyperplane is one of the important ones is d over n. Yes? Boy, I wish I could see the nodding heads. Feel free to turn on your cameras if you like, so I can see your heads nodding. But hopefully this is clear. You'll have to ask a question if something is not clear, because I can't tell otherwise. All right, so this is a very small number, right? Because we're assuming d is a small constant. So we almost never have to update, which is great. But there is still the problem of, well, we have to update. So what's really nice about Seidel's algorithm is that in the previous cases, when we looked at the violators, we said we have this set of violating hyperplanes, but among that set is an optimum hyperplane, right? Now, with Seidel's algorithm, since we only have one violating hyperplane, what do we know? We know it is, in fact, a part of the optimum basis, right? So when we update, we know that that last H is in the basis. How can we take advantage of that? Jofi.
Well, we then have to choose which one of the existing bases to throw away.
Well, we only have this one. Sorry, we have. Okay, good. So let me, I may be interpreting your thinking wrong, but let me try this. You're saying we have this optimum of the n-1 hyperplanes, right? And now we have this one other hyperplane that violates, right? And so the natural thing to say is, well, we just need to get rid of whichever was the wrong hyperplane in the current basis so that we can replace it with this last hyperplane, which belongs in the current basis. And if that were true, then linear programming would be a lot easier.
Oh, fair.
The problem is that we know that this hyperplane belongs in the basis, but we don't know that, like, the optimum that we found among the n-1 hyperplanes, those hyperplanes, there might be more than one of them that's not part of the optimum basis, right? So I could be in a situation where, let's see, can I draw this quickly? That we have down here 2, and we have up here a different 2. And the result is that if I take this last H away, it completely moves the optimum. All right. So how do we use the fact that that we have one hyperplane of the optimum? Well, that tells us that we only need to find d-1 other hyperplanes in order to find the optimum. We're no longer looking for d hyperplanes. And in particular, this tells us that the opt is on H, is on that last hyperplane. Yes? So if that opt is on the last hyperplane, like again, if you think about how you go about solving a system of equations, once you know, once you have an equation, you can use that to get rid of a variable, right? So we can project the entire LP onto this hyperplane H, right? Because we basically, we take each constraint and we intersect it with H. And that gives us a constraint hyperplane of one less dimension in H. Is that clear? Sorry, it doesn't really make sense for me to ask these questions because I can't see you nod. So tell me if it's not clear. So we take this hyperplane that we know is optimal, we project the linear program onto it. Now we have a d-1 dimensional linear program. And so on this, we recurse in order to find the optimum. Okay. So this gives us a beautiful recurrence. The time to solve a linear program of n constraints in d dimensions is at most the time to throw away one hyperplane and solve, plus the interesting term, with probability d over n, I'm going to have to do a recursion. And how much is that recursion going to cost me? Well, I'm going to have to do a bunch of projection work. And then I'm going to have to solve a d-1 dimensional linear program. Okay. And this turns out to have a solution of d factorial times n. Okay. Basically, the first term, t of n-1, d-1, is going to cost you d factorial times n-1 by induction. The second term is going to be d over n times this order dn plus d minus 1 factorial times n. But what's lovely is we have an n in the denominator canceling out the n's on the inside. So this is d times d plus d minus 1 factorial. And this is negligible and gets swallowed up in the constant of the O, and that's why it's a d factorial n running time. Any questions about that? So this is gorgeous, right? A 4-line algorithm and a 2-line analysis. So I don't think it is possible to invent a simpler linear programming algorithm than this. Now you'll notice that its runtime is a little bit worse than what we were able to achieve with the iterated sampling in terms of D. It's got a d factorial multiplying the n, whereas iterated sampling only had a d squared multiplying the n, and it had a separate exponential in D term. So that one was only additively exponential in D. This one, the exponential term multiplies n, so it's arguably a little worse for larger D, but it is so simple and so beautiful. And in fact, it even gives us some other really nice insights. This also gives us a simplified proof of our main sampling theorem that we used for the iterated for the previous algorithms. And I showed you that esoteric proof, with that really clever switch in the binomial coefficients, because that's how they figured it out first. But look how easy it is if we think the way Seidel did. We want to argue that we want to analyze what happens when we choose R random hyperplanes R, and then ask how many hyperplanes violate or violated by the optimum of that random set, right? That was the key sampling theorem that we used, right? So I'm going to analyze this with a sort of backwards analysis. What I'm going to say is let's say V is equal to the number of violators. Okay. Now V is a random variable, okay, but it does have an expectation. And one way for me to understand that expectation is to instead think about P, which is the probability that a random hyperplane H that is not in the set that we first choose is a violator. Right? If I tell you that there are V violators, then what is the probability that a randomly chosen hyperplane not in the sample is a violator? Someone just shouted out so that I know that I'm still connected.
V over n, or like
Yeah.
V over number of things not in the sample.
Exactly. It's V over n minus R, right? Now, as I said, V is a random variable, but I can talk about the expected value of P as the expected value of V divided by n minus R, right? Which means that the expected value of V, which is what we care about, is just the expected value of P times n minus R. So if I can tell you what P is, then I can tell you what V is. Okay, and I'm going to do that using a backwards analysis. So the way I've asked this question, I said, first you pick R, and then you pick H, and ask if this H is violating the optimum of R. Okay, so instead, to analyze this very straightforwardly, I'm going to choose at random R together with H. And then from it, choose my H at random from the previous set, right? So essentially my experiment involves choosing a total of R+1 hyperplanes. And one way to do that is to first choose the R hyperplanes and then choose one more. I'm going to do it the other way around. I'm going to choose R+1 hyperplanes and then randomly decide which of them is left out. Okay? So if I think of it in this backwards perspective, what is the probability that H violates the optimum of R? Dubin.
Only like D of them actually define the optimum. So then it
Exactly,
should be something like
right?
that.
Whatever the optimum of, right? So basically, if H is one of the hyperplanes that the only way for H to be a hyperplane that violates the opt of R is if H is a part of the opt of R union H. Sorry, that doesn't actually make sense symbolically. Let me say R with the extra, right? So the only way to get a hyperplane that violates is to take away one of the hyperplanes that defines the optimum of the whole thing, right? And so that probability is only D over R+1. Yes? So now we have that P is equal to D over R+1, which tells us that the expected value of V is equal to D over R+1 times N minus R, which is basically the same number as we got from the complicated analysis that we did last time. Any questions? Dubin.
I feel like I have a question. I'm just like not sure as I want to ask, but I guess it just like it feels a little strange to like do like do it like do this backwards, I guess, because like
Yes,
what
it feels very strange. And that is what I am trying to teach in this class, is this way
yeah
of thinking about things in very strange ways, because
yeah
they do work.
yeah
Right? So again, we are describing exactly the same probability space two different ways. So it's kind of like when you invert the order of summation, right? You just think of two different ways of looking at exactly the same thing. So the natural way to describe it, because it's sort of chronological, is that I am choosing a random R and then I am following it by choosing a single H, right? But the easy way to analyze it is to describe exactly the same probability space in a different way, which is that I am starting by choosing R+1 hyperplanes, and then I am randomly calling one of them H, right? It has exactly the same distribution over sets of R's and H's.
okay yeah that makes sense. Okay.
Isn't this beautiful? I like I was in grad school when Seidel did this, and I was like, wow. Any questions? We're not actually done with these insights yet. We're going to do even better by thinking about how we can tweak Seidel's algorithm. And this goes back to a question that was asked, a very smart question that was asked by somebody in class on Monday, which is, all of our analysis talks about how, you choose this sample and it must contain a violating it must have one of the optimum hyperplanes violating the optimum of the sample. But isn't that very pessimistic? Why would you think, like, if you get many hyperplanes from the optimum violating the sample, then you suddenly make a lot of progress all at once. And isn't there some chance of that happening? And shouldn't we incorporate that into the analysis? And that is what we will do as our next step. But let's take a break for a few minutes to recharge. I will resume when my clock says 12:27, which is in about 2.5 minutes from now. And now, since I've been sitting, I'm going to stand up as well. And you should too. All right, let's resume. I'm going to start with logistics. I'm going to still be at this conference on Friday. And I just want to confirm that people are sort of valuing this Zoom-based approach as opposed to watching a recording. So if you would like to a redo of this on Friday, raise your hands so I can just take account of and make sure there's a critical mass for the Zoom lecture again. All right, that may not be enough. Let me see. People may be coming back slowly, so let me check if at the end of lecture whether people want to redo on Friday. Let's continue on our narrative around faster linear programming algorithms. The next idea that progressed here is something called hidden dimension, which was developed by Scherer and Welzel. Sorry, the one problem with this app is that it's really bad at erasing. And so actually, so this whole story, like Clarkson's original sampling-based linear programming algorithm was in 1988. And we're going to get to the sort of end of the story around 1992. So there was this flurry of progress in the late 80s, early 90s that gave all of these ideas. And they introduced an idea called hidden dimension. And their idea is to look more closely at Seidel's algorithm. Okay. So again, I wish I had like a 5-dimensional blackboard where I could convey some of these ideas more clearly. So Seidel's advantage was that, you know, when we emitted this hyperplane, we knew that it was in the optimum, so we only needed to find d-1 other constraints of the optimum. But what if there are a whole bunch of other parts of the optimum solution in that recursive opt that we found, right? Then we should be able to take advantage of this in some way. Okay. So use more optimum hyperplanes if we can somehow find them. And we're not actually going to literally find them, but we're going to have supersets that contain them. So let's suppose that the optimum basis is these D hyperplanes H1 through HD. I'm going to order them in a funny way. We've got opt of H, which is large, right? Because all of the, sorry, opt of capital H, which is large because all of the hyperplanes are there. They're lifting the optimum very high. If I take some hyperplane, if I take a hyperplane away, the optimum drops. And I'm going to put the, I'm going to use HD to represent the hyperplane where the optimum drops the least. And I'm going to work my way down as I think about different hyperplanes. Removing each of them drops the optimum by some amount until we get to H1, which drops the optimum by the most. Okay, so that's just a particular ordering of the hyperplanes. And remember, we're assuming general position here, so all of these opts are different and all of these inequalities are strict. Okay. Now, the recursion happens. We recurse if we dropped as our final hyperplane some H sub j. Yes? Now, that means that we found the optimum of H minus H sub j. Now, what I claim very conveniently is that H1 is in the basis that we found when we discarded H sub j. Okay. And the reason is pretty simple. Suppose it's not. Okay. If H1 is not in the basis, that would mean that I can throw away H1 as well without changing the optimum basis, right? It means that the optimum of H minus Hj is equal to the optimum of H minus Hj minus H1. Yes? But we also know that the optimum of H minus H1 is greater than or equal to the optimum of H minus H1 minus Hj. Why do we know this fact? Balint?
Well, because removing hyperplanes can only like decrease the optimum.
Exactly. Removing a constraint makes things better. So if we remove hj from h minus h1, it doesn't make the optimum worse. Okay. So if you combine these two simple facts, it would tell us that the optimum of h minus h sub j is greater than or equal to the optimum of, the optimum of h minus h1 would be greater than or equal to the optimum of h minus hj. Right? Because we know that the opt of h minus h1 is bigger than the opt where you've taken away both, but we also know that the opt where you've taken away both is the same as the opt when you just take away hj. Okay, but this is contradicting the ordering of the h's, right? Because h1 is the h that drops you the most when you take it away. Okay, so basically, if you throw away, and I made the argument about h1, but it applies to any hyperplane that precedes hj in the ordering, right? So in fact, what this tells you is that all of h1 through hj minus 1 are in the basis of h minus h sub j. So we don't only get one hyperplane, we get lots. We don't get one of the optimum hyperplanes, we get lots of them. Okay. And which of these hyperplanes are we likely to throw away? Or what is the probability we throw away any of these hyperplanes? Well, it's uniform, right? We're choosing a hyperplane uniformly at random. So in fact, in expectation, right, the basis without this random, that where we throw away one hyperplane contains d over 2 of the optimum hyperplanes. If we need to do an update at all. Okay. So we are going to use this in a recursive algorithm. And this is an algorithm called basis LP. I didn't make up these names. They're just what's in the Madhwani Raghavan textbook. Someday I'll think of cleverer names for them. Basis LP works with an input of hyperplanes H and a helpful basis T. I'm going to show you in a minute how it is helpful. It is a kind of a hint, giving us guidance towards what is the optimum. So the first thing that we do is we check if if we only have D hyperplanes, then of course we're done. We have the basis because there's only one basis. Otherwise, we're going to pick a random hyperplane from H, but we're speculating that T has lots of the optimum basis in it. So since we think that T has a lot of the optimum hyperplanes, we're just going to avoid choosing from T. And that is going to reduce our chances of picking an optimum hyperplane, which will reduce our chances of having to repair the optimum in that backwards analysis. We then compute a new basis T prime by computing recursively. So this is sort of Seidel's algorithm, where we throw away one hyperplane and we recurse. Okay, it's just that we are recursing with this hint now. Now, what's interesting here is that because we avoided because we avoided t, it's going to change the odds that we have to update, but there still is a chance that we have to update, right? If the hyperplane that we threw away doesn't violate t prime, then we're done. Okay. Otherwise, we return basis LP of the complete set of hyperplanes. Whoops. Complete set of hyperplanes. But now we give ourselves a better hint by optimizing with T prime and also this last violating hyperplane. Okay. So notice that T prime unit H is just D+1 hyperplanes. So computing its opt is not very hard. You basically try throwing away each hyperplane and compute the resulting vertex, and you get D+1 vertices, and you see which one of them is the best, or is the optimum. Okay. So computing the new hint is trivial, and you use that new hint in your recursion. Okay. And what we're going to show is that you rapidly get lots and lots of the optimum constraints into your hint, so that you don't have to do many corrections. Okay. So any questions about the algorithm? If not, I'm going to go on to the analysis. So to analyze this, we are going to say that a constraint is enforcing if the optimum without that constraint is less than the optimum of our hint. Okay. Now, first of all, it is clear that H has to be in T. Why is that? So looking at the definition of enforcing, what happens if you throw away a constraint of H that is not in T? Well, that means that all of T is still part of your hyperplanes. So if all of T is still part of your hyperplanes, what does that mean? Balint?
Well, if all of t is still in the set, then the optimum can't possibly be better than opt of t.
Exactly. If T is part of H minus H, then the optimum of T is better than the optimum of H minus H, because throwing away constraints only improves your optimum, or adding constraints only worsens your optimum. The second claim is only slightly harder to prove. H is actually part of the optimum. And the reason for that is that if H is not in the basis, then the opt of H without that hyperplane is equal to the optimum of H. But we know that the optimum of H is greater than or equal to the optimum of T. Yes?
Don't we
So we,
explicit? Or
sorry, go ahead.
oh, sorry, I thought you were saying yes to my question, but don't we normally don't we pick H to not be in T? Like, isn't it like H minus T? So then,
Uh, this is this is a sort of sub statement about an arbitrary hyperplane. It's not the hyperplane that we chose in the algorithm.
okay, and so we're saying if it's enforcing, then it's in T.
Yes. So
Okay.
whatever the current state of our algorithm is, right? Again, our algorithm takes H and T as inputs,
Mhm.
right? And so whatever H is and whatever T is, any enforcing hyperplane for that H and T is in T and in B of H. So in fact, it is in T intersect B of H. Yes? So certainly that means that there are at most D of them. Because it's an intersection of two sets of size D. And if there are exactly D of them, then it must be the case that T is equal to B of H, and we're done. Because that's the only way that the intersection could be of size D. Okay. So moving on some more. We now define the hidden dimension. Which is just equal to, this is the hidden dimension of T. It's just equal to D minus the number of enforcing constraints. Which basically means it's the amount of B of H missing from T. Okay? Because the enforcing constraints are in B of H and in T. So if you subtract from D, if you subtract D from that, you find out how many things are not part of B of H in T. Okay? And this dimension is going to drop. And if it's 0, we have found the optimum. Okay. But now notice, the algorithm discards a hyperplane not in T. So only this hidden dimension number of optimum hyperplanes can be discarded. So if the hidden dimension of T is very small, then we are very unlikely to discard one of the optimum hyperplanes, right? Where sort of T is safeguarding a set that we think has a lot of the optimum hyperplanes in it. So we don't discard from there. And that means that our chances of discarding an optimum hyperplane are very small. They're just equal to the hidden dimension divided by n, right? So the probability that we have to do a fix is at most the hidden dimension divided by n minus d. Okay. So now the next claim is that if we have to fix, then the hidden dimension drops. In the recursive call. So remember that in the recursive call, when we have to do a fix, we are going to compute, we're going to recurse, but we compute a new hint. We compute the optimum of T prime together with H. And the claim is that it has a better hidden dimension. Okay, because T prime has a better opt than T. Okay, and that means that all previously enforcing constraints for T are also enforcing for T prime. And we also know that the left out constraint that we need to fix is enforcing, because otherwise we wouldn't have to do the recursion at all. So T prime has at least one more enforcing constraint, but this is where we use the fact that we can get lots of constraints all at once. Okay, so in general, we're going to get many constraints. So suppose that we have this hidden dimension. We have constraints of B of H that are not yet in T. As we discussed above, we order them by the optimum of by how the optimum changes when we take away those hidden optimum constraints. By backwards analysis, we're equally likely to leave any one of them out. So we're equally likely to pick any one of them. And as above, if we pick the rth in our order, then all of H1 through HR, so I guess I should say if I pick HR in my order, then all of H1 through HR are enforcing and added to T prime. Okay. So now we can write a recursion for the hidden dimension, which says that we do a recursion where we've thrown away one hyperplane. Sorry, this is an M. So we throw away one hyperplane in recurse, just like in Seidel's algorithm. But then our chances of making a mistake are about, let me write it out and then we'll discuss it. Sum from I equals 1 to k minus 1 of T of n comma I. So this recurrence says that we get a sort of uniformly distributed hidden dimension in the second recursive call, right? If we pick H1, then the hidden dimension only drops by 1. If we pick H2, then the hidden dimension drops by 2. If we pick H sub m, then the hidden dimension drops all the way to 0. And all of these picks are equally likely. And each of them happens with probability 1 over n minus d, because that's how many hyperplanes we're choosing from. And if you solve for this, it turns out you can plug it in order to see if this is true. T of nm is at most 2 to the m times n minus d. Okay. And essentially what the reason that works is that this inner sum is a geometric series whose last term is 2 to the m minus 1, which gives you your 2 to the m for the next layer. Okay? So the summary, this is definitely the hardest analysis that we've done today, or on Monday, but it replaces the d factorial in and so if we start with a d-dimensional LP, even if we start with an arbitrary basis, the hidden dimension is only d, and so the runtime for d-dimensional linear programming is now 2 to the d times n instead of d factorial times n. So it's exponential in d, but it's at least not d factorial. Now, this seems like a lot of work for a small improvement, but it turns out that we can go yet farther. I'm not going to do that today, but I'm going to tell you where we are headed, which is we want a sub-exponential linear programming algorithm. So everything that we've seen so far is something to the power of d. And so the question that remains is, can we make it something to the power of something that's smaller than d? And I will take a few minutes on Friday to show you that the answer is yes. And then we will move on to our next topic, which is generally known by the phrase the probabilistic method. It is about solving problems by generating random solutions. So it's not the same as random sampling. We are not going to generate a solution that tells us something about the optimum and then use it to find the optimum. Instead, we are going to be looking at generally NP-hard problems and showing how a random solution has a decent chance of being a good solution if you generate it if you use the right probability distribution for the randomness that you are for generating that random solution. Obviously, if your probability distribution chooses the optimum solution with probability 1, then it's a very good probability distribution. But we are going to show how to come up with computable probability distributions that produce results that are pretty good. So that will be the focus of Friday's lecture, after I give you another 15 minutes on getting even better at our linear programming algorithms. So are there any final questions? All right, then I will see you on Friday.